Welcome to the University of Arizona Global Campus, Future Graduates on Coffee podcast.
Episode 1, Week 1, Database Management Systems.
Welcome to the deep dive. Today, we are plunging into, the essential structures that really underpin our entire digital lives.
Mm-hmm.
I mean, just think about the sheer scale of modern existence, right? Everything you do, from your birth certificate to, your last online purchase, it generates and consumes data.
Constantly.
We are talking about this enormous, persistent, just pervasive trail of facts. It's like a data tsunami that never stops.
That's absolutely the right way to frame it, yeah. Data isn't just abundant, it is fundamentally the critical raw material that organizations rely on, not just to survive, but to innovate.
Right.
Imagine trying to run, say, a global logistics company without instantly knowing where every single shipment is.
Impossible.
Or a major bank without accurate real-time records of every single transaction. It's an impossible scenario today. Data has to be available, it has to be timely and accurate for any meaningful decision-making.
And that availability, that speed and accuracy, that's not achieved by just, stacking digital files higher and higher.
No, not at all.
We're talking about systems operating at absolutely astronomical speeds. Think about, telecommunications companies tracking trillions of connections. They're adding new data at peak speeds of tens of thousands of records per second.
Yeah, the scale is mind-boggling. Or Google processing data volumes measured in petabytes just to give you search results in milliseconds.
Wow.
The ability to manage that scale, that complexity, and just the sheer speed. It requires specialized organizational structures. You can't use a shoebox for the Library of Alexandria.
Good analogy. Okay, let's unpack this then. Our mission today is basically your shortcut to understanding those specialized structures, the databases, that store, manage, and retrieve this massive influx of facts quickly, reliably. We're tracing the blueprints, from the clumsy file folders of yesterday all the way to the sophisticated big data models of today to really show you why this foundational technology matters more than ever. Okay, so before we can even talk about the structures that hold all this data, we really need to nail down our core vocabulary.
Good idea.
Because in everyday language, we tend to throw around data, information, and knowledge almost interchangeably, right?
We do, yeah. But in computer science, especially in data management, they represent a very precise three-tiered hierarchy.
Okay.
So we start at the bottom with data. Data, by definition, is just raw facts. Simple as that. They're facts that haven't yet been processed to reveal any meaning to the end user.
Raw facts.
Think of them like individual pieces of a massive jigsaw puzzle just scattered all over the table. No picture yet.
Okay, give us a concrete example, something that really highlights that raw nature of data.
Okay, let's use the university faculty example.
Right.
Imagine you have this massive spreadsheet, right? Thousands and thousands of entries. Names, employee IDs, departments, hire dates, salaries, specific roles.
Just rows and rows of stuff.
Exactly. If you just scroll through those hundreds, maybe thousands of rows, you gain virtually no insight, no understanding of the institution's overall staffing strategy or anything really. Those individual context-free entries, that's raw data.
Got it. So, information.
Yeah.
That's the next step up. That's where we start getting some insight.
Yes, information is the result of processing those raw facts. Now, this processing could be simple, like, just sorting or adding things up, or it could be highly complex, involving statistical models, things like that. But the key transformation is that information requires context to reveal meaning. And it's that meaning that facilitates decision-making.
Right. The context piece feels crucial. Like, if I just tell you a temperature reading is 105 degrees,
yeah,
that's raw data. But if I don't give you the context, is it Fahrenheit or Celsius? Is it, body temperature or machine's temperature or the outside air? That data point is basically useless.
Precisely. The context is what turns those raw facts into something usable, into information.
Okay.
And tying that back to our faculty example, when you process that raw data, maybe generate a summary, like an aggregated report showing that, say, 20% of the entire information systems department faculty are adjunct.
Oh.
And maybe that percentage has grown 5% year over year. That summary, that report, that's the information derived from the data. It's a decision-making tool now.
Got it. And then we move to the top of the pyramid. We hear this phrase a lot, moving into the knowledge age. So what makes knowledge distinct?
Knowledge is really the ultimate understanding. It's the body of information and facts about a specific subject, but it implies familiarity, awareness, a really deep understanding of that information as it applies to an environment.
So it's information plus experience almost.
Kind of, yeah. Knowledge is the bedrock built upon information. And what's really crucial here is that knowledge allows for prediction and extrapolation. You can often derive new knowledge from old knowledge.
That sounds a bit abstract, maybe, but this whole process, data to information to knowledge, it happens millions of times a second right on our phones, doesn't it?
It absolutely does.
Let's trace that path through the predictive smartphone example. How does that work?
It's the perfect illustration, really. So your smartphone's GPS, it's recording your whereabouts constantly. That daily stream of coordinates and timestamps, those are the raw facts data just being stored away, gigabytes of it.
Okay, just raw location point.
Right. Then the processing starts looking for patterns in that stream.
Ah, so the phone starts to figure things out.
Correct. The system processes that raw data, and it starts recognizing patterns across time and space. Like, okay, every Thursday at 7:15 a.m., this user drives to location X, which we'll label work.
Right.
This recognition of routine based on aggregating all those data points, that's the information being derived.
Okay, so it knows my routine, and then the final payoff is that powerful predictive knowledge.
Exactly. The system learns these patterns so well that maybe 20 minutes before you'd typically leave for the gym on a Tuesday evening, it pops up a message. Hey, 18 minutes to the gym, traffic's a bit heavy today, maybe leave now.
Wow.
That advice, that predictive action, that is the knowledge. It's timely, it's relevant, and it's derived entirely from processing timely and accurate data.
Okay, so the key takeaway here, before we move on, is really this. That whole pyramid data, information, knowledge, it just collapses if the base is unstable.
Absolutely.
Knowledge and information are basically worthless if the underlying data isn't timely, accurate, and crucially for our conversation today, properly stored and accessed.
That's it. And that explains precisely why data management is such a critical discipline in, well, any modern endeavor.
Okay, so we've established data management is essential. But organizations haven't always had these sophisticated databases, right? Let's look back a bit at the historical context, starting with, well, the evolution from paper records to those early computerized file systems.
Right. Historically, businesses ran on manual systems, literally folders, paper ledgers, filing cabinets, mountains of paper.
I remember those.
Yeah. And as organizations grew, that just became completely unmanageable. So they moved to computerized file systems. These were typically managed by specialized data processing or DP departments. This was really the first crack at digital organization.
Okay, so for context, what did these early digital files actually look like? What were the basic components?
Sure. There are 3 basic terms we need. A field is the smallest unit of data. Think like a customer's name or a part number, just one piece of info. Then a record is a logically connected set of fields that describes one instance of a person, place, or thing. So everything about one specific customer would be a record.
Name, address, phone number, all together.
Exactly. And finally, a file is just a collection of related records. So you'd have the complete customer file or the inventory file and so on.
Okay, so these computerized files, they solve the paper problem, the physical storage issue, but they introduced a whole host of new systemic failures that made the system, well, ultimately untenable.
Oh yeah, big time.
Let's start with the administrative nightmares.
Yeah.
What were the big pain points?
The pain points were immense. I mean, first, lengthy development times. If a manager needed a new report, even a simple request like, show me all customers in California, it required the DP specialist to write extensive, specialized programming code from scratch.
Why from scratch every time?
Because the system lacked what we call non-procedural languages. The programmer had to specify what data was needed and precisely how the computer needed to step through the files, navigate the structure to actually retrieve it. Very low-level stuff.
Okay, and that sounds like it leads directly to the next issue. Ad hoc queries. Spur-of-the-moment questions.
Right. Forget about it. An ad hoc query, just a quick, hey, how many units of product X did we sell last Tuesday? Impossible. Because the programmer had to custom write code for every single request, they just couldn't answer these immediate questions.
So what happened?
Reports were constantly delayed. You'd hear, yeah, we can get that for you next week or maybe next month, which of course rendered the resulting information totally useless for immediate tactical decision-making.
And as organizations grew, the system administration itself must have scaled horribly.
Oh, it was a management disaster. See, different departments often owned their own data files.
Right, silos.
Exactly. Islands of information. And each file required its own separate set of management programs just for the basic tasks. Adding a record, changing a record, deleting one, listing them out.
So For every file, you needed multiple programs.
Yes, and as you added more files, which happened constantly, the administrative burden just multiplied exponentially. It led to incredibly complex system administration.
And for the listener, this probably meant the data wasn't very secure and it was hard to share.
Exactly. Lack of security and limited data sharing was a massive flaw. Security features, like passwords or maybe restricting access to certain fields like salary.
Yeah.
They had to be hard-coded into each individual application program by the programmer. If the programmer forgot or just didn't bother, the data was wide open.
Wow.
And yeah, data was totally isolated in these departmental islands of information. Sales couldn't easily see inventory data. Marketing couldn't easily see sales results. It was inefficient.
Okay, now here's where we get into the real structural rigidity, the dependence issues. Let's tackle structural dependence first.
Right. Structural dependence means that access to a file is rigidly dependent on its specific physical structure, how it's laid out on the disk.
Okay, give me an example.
Picture this. The IT department decides they need to add a new field to the customer file. Let's say Suey's mail. Seems simple, right?
Yeah.
But because every existing program that used that file was written to look for data at specific physical locations within the file structure, adding this one new field meant you had to find and modify every single application program that touched the customer file.
Oh my God. Every single one.
Every single one. That's a monumental maintenance cost just for adding an email address. The goal, therefore, had to be structural independence, where programs aren't tied to the physical layout.
Okay. And then the twin problem is data dependence. Similar idea.
Similar, yeah, but this deals with the characteristics of the data itself, not just its position. So if you decided to change a field's data type, say, a product code needed to go from storing maybe 4 digits, an integer, to storing 5 alphanumeric characters.
Right, maybe adding letters.
Exactly. You'd have to change every program that accessed that product code field to handle the new format. In these old file systems, the logical view, how humans think about the data, and the physical view, how the computer actually stores it, were just tragically intertwined. We needed data independence.
But the source of, probably almost all the headaches, and the thing that really made the data utterly untrustworthy was the redundancy trap.
Ah, yes. This was the devil in the details, truly. File systems actively encouraged rampant data redundancy, which just means the unnecessary storage of the exact same piece of data in multiple different places across different files.
Like the agent's phone number being in the sales file and the personnel file.
Precisely. The sales file needs the agent's name and phone to contact them. The personnel file needs the exact same information for HR purposes, so you store it twice, or maybe 5 times across different systems.
Why is that such a huge problem? Isn't having backups good? Why can't we just have 2 copies?
It sounds okay, but it leads to 3 immediate, really destructive consequences. First, poor data security, simply because there are more places you have to protect the same sensitive data.
Makes sense.
Second, and this is huge, data inconsistency. If that agent changes their phone number and personnel updates their file, but the sales department forgets or updates it incorrectly, you now have 2 different conflicting versions of the truth floating around. Which one is right?
Nightmare.
Absolute nightmare. And third, data integrity problems. This means the data fails to conform to the basic rules it should. For instance, an application might let a user enter an invoice for a customer ID that doesn't actually exist in the main customer file because the checks just weren't there or weren't consistent.
And this structural chaos, this redundancy, it actually manifested in specific ways, didn't it? What we call data anomalies, these abnormal conditions that just make data systems fundamentally unreliable.
Exactly. Anomalies are the direct result of that redundancy.
Let's start with the one you just kind of alluded to, the update anomaly.
The update anomaly is the absolute poster child for redundancy failure. Using our agent example, if Agent Leah F. Han changes her phone number, and maybe that number is stored not just twice, but in 500 different customer records across various files, you have to manually find and update all 500 of those instances correctly. The potential for missing just one or typing one, creating that data inconsistency we talked about, it's practically 100%.
Okay, wait. If redundancy is the devil, what's the single most destructive thing that can happen when we try to add a record? Is there a problem there too?
Oh, absolutely. That would be the insertion anomaly. Let's say you needed to add a brand new sales agent to the system. They just got hired.
Okay.
But maybe the only file structure you have stores agent data with customer records in the customer file. If that new agent hasn't been assigned any customers yet, You literally cannot add them to the system.
Just serious.
Seriously, unless you create a fake dummy customer record just to attach the new agent's information to. You are forced to create inaccurate data simply to satisfy the flawed file structure.
That's madness. Okay, and the final. Maybe the most painful anomaly.
Yeah.
The deletion anomaly.
This one is just, it's the data management equivalent of accidentally throwing away the keys to the kingdom while you're just trying to tidy up.
How does that happen?
Let's say you delete a customer record. Maybe that customer stopped doing business with you, fair enough.
Right, clean up the files.
But what if that customer happened to be the only customer served by a specific, maybe part-time agent? By deleting that last customer record associated with the agent, you inadvertently delete the only record of that agent's existence in that file. Maybe their name, commission rate, everything related to their sales activity.
Poof, gone.
Gone. You delete essential business data just by doing routine housekeeping.
So the file system was just,
Yeah.
It was a maintenance nightmare, a huge security risk, totally inflexible, and just riddled with inherent inconsistency because of redundancy and these anomalies. Clearly something had to change. A major structural change was needed to make sure the foundational data was actually trustworthy.
Exactly. The pain became unbearable.
Okay, so the chaos and the pain of those old file systems really ushered in the age of the database system. This offered a way out of that redundancy trap by providing what logically related data stored in a single integrated repository.
That's the critical distinction, yes. Integrated. A database is defined as a shared, integrated computer structure that houses a collection of related data.
Okay.
And crucially, it stores two types of data that are key to its success. First, the end-user data itself, the raw facts we care about, customer names, product prices, etc.
Right.
And second, perhaps most importantly, metadata.
Metadata. Okay, that sounds like the secret sauce here. You mentioned it earlier. Data about data. Is that what gives the designer the power to change things without breaking the whole system?
Absolutely. Metadata is what makes the database self-describing. It contains the definition of the data elements, their names, their data types, is it numeric, a date, text, whether they're required fields or not, their length, any constraints.
Ah, so it describes the structure.
Exactly. And this structural description, the metadata, is stored separately from the raw data itself, usually in a data dictionary. This allows the system, the database system itself, to know exactly what the data is supposed to look like without relying on each individual application program to define it over and over again.
And that separation, that centralized definition that allows for the gatekeeper, right?
Right.
For the database management system, or DBMS.
Precisely. The DBMS is the collection of programs that manages the database structure and controls all access to the data stored within it. It is the absolutely necessary intermediary.
So the data is still stored in physical files somewhere.
Yes, deep down, the underlying data is stored as physical files on disk. But the only way for users or application programs to get at that data is through the DBMS. It acts like a translator or maybe a traffic cop.
Okay.
It presents a single, integrated, logically consistent, and simplified view of the data to everyone, while completely hiding all the underlying complexity of the physical storage, how it's indexed, where it lives.
Okay, so having this intermediary system, this DBMS, must provide massive advantages over those old chaotic file systems. What are the most immediate, powerful benefits for an organization that adopts this?
Well, first and foremost, the ability to answer those immediate questions we talked about. You get improved data sharing and access. This enables quick, real-time answers to ad hoc queries.
Right, the manager needed to know about product X sales last week.
Exactly. In the file system, that was maybe next month. With a DBMS and a query language like SQL, that's potentially seconds. A huge difference.
Okay, what else? This sounds like it completely revolutionizes system administration and accountability too.
It really does. Because the data is integrated and managed centrally, it fosters better data integration. You get a much clearer, unified view of the organization's operations. And critically, it minimizes data inconsistency because the data is ideally stored only once, or if there's planned redundancy, it's managed centrally by the DBMS.
No more conflicting phone numbers.
Hopefully not. Furthermore, the DBMS provides a robust framework for improved data security. It allows for much better, more consistent enforcement of privacy rules and access controls across the entire dataset, not just hoping each individual application programmer remembered to add security checks.
Okay. And for the folks in the C-suite, the executives, this translates directly to better strategy, right?
Exactly. Improved decision-making is arguably the ultimate goal. Better managed data yields better quality information, period. The DBMS is the core technology that supports data quality initiatives, making sure that data is accurate, valid, timely, and that higher quality information directly informs better, more confident strategic choices.
Makes sense. And what about the people actually using the system day to day, the end users?
They see a huge benefit too: increased end user productivity. The DBMS provides tools like report writers and query interfaces that transform that raw data into usable information rapidly. It empowers users to get answers and make quick, informed decisions themselves without needing a programmer to write custom code for every single little request. It really democratizes access to information within the organization.
Okay, so we have the DBMS managing the database, but not all databases are built for the same job, are they? I imagine they can be classified in multiple ways, like by scale or location or what kind of data they hold or what they're used for.
That's right. There are several useful ways to categorize them. Let's start with the human scale first: number of users and physical location.
Okay.
By the number of users, the simplest is a single user database. That's typically what you'd call a desktop database running on a personal computer, used by just one person at a time.
Like Microsoft Access, maybe?
Yeah, that's a classic example. Then you scale up to the multi-user databases.
And even within multi-users, there are distinctions based on size, right?
Yeah. Yes. We generally talk about a workgroup database, which typically supports fewer than 50 users simultaneously, or maybe it's confined to a single department or a specific workgroup.
Yep.
Then you have the enterprise database. This is the big one, used across the entire organization. It supports hundreds, maybe thousands of users concurrently across many different functional units: sales, manufacturing, HR, everything.
Okay, that's users.
Uh-huh.
What about location? We started with databases being in one place, didn't we?
Right. Traditionally, you had the centralized database where all the data lived at a single physical site, one main computer or server cluster.
And then it's got more spread out.
Yep. Then came the distributed database. Here, the data is actually spread across several different physical sites, maybe different offices or data centers, connected by a network.
And the massive modern shift, of course, is
The cloud database. These are databases created and maintained using cloud computing services. Think Microsoft Azure, Amazon AWS, Google Cloud Platform.
and the big advantage there is agility, isn't it? Not having to own the hardware.
It's absolutely transformative for infrastructure management. Organizations no longer have to worry about buying, installing, configuring, or maintaining the underlying servers and storage. They just purchase the required storage and processing capacity they need when they need it from the cloud provider.
That sounds incredibly flexible.
It is. The example we see is huge. 3M Health Information Systems, they consolidated multiple legacy IT centers. By moving their database operations to AWS, they reportedly cut their server provisioning time getting a new server ready from 10 weeks down to just minutes.
10 weeks to minutes.
Yeah, that kind of speed enables incredible business responsiveness.
Okay, let's pivot now to classification by the intended usage of the database. This seems really key to business strategy.
It is. You have two main types here, and they're designed for fundamentally different jobs. First, there's the operational database.
Operational, like day-to-day operations.
Exactly. This is also called the Online Transaction Processing Database, OLTP, or sometimes the Production or Transactional Database. Its primary focus is supporting the day-to-day operations of the company.
So recording things as they happen.
Precisely. Recording accurate and immediate transactions. Think of processing a single sale, recording a payment, making an ATM withdrawal. It needs to be incredibly fast, reliable, and consistent for these moment-to-moment activities.
Okay, so if the operational database handles the immediate present, what handles looking at the past and maybe predicting the future?
That's the domain of the analytical database. This type of database is focused almost entirely on storing historical data and business metrics. Its purpose is for tactical or strategic decision-making, looking for trends, patterns, insights.
So it's not for live transactions.
No, typically not. And because the data isn't needed for live second-by-second operations, it often requires extensive manipulation, or what's sometimes called data massaging, to get it ready for analysis, summarizing, aggregating, cleaning it up.
And this area includes specific components, right?
Yes. This analytical database area typically comprises two main parts. The data warehouse, which is the large, centralized repository storing all that historical and aggregated data, often from multiple operational systems.
Okay. And the online analytical processing, OLAP, tools. These are the software tools used to query the data warehouse, slice and dice the data, create multidimensional views, and extract those patterns and insights. This whole discipline, combining the data warehouse and OLA, is now commonly known as business intelligence, or BI. Got it. Okay, one last classification. We have to address the structure of the data itself, because that structure, or lack thereof, has created the need for entirely new kinds of databases, structured versus unstructured.
Right. This is a huge distinction now. Unstructured data is basically data in its original raw state. Think of a raw text document, like an email or a report or a video file, an audio file, an image. It doesn't have a predefined format or organization, so it doesn't lend itself to immediate processing by traditional methods.
Okay, so what's structured then?
Structured data is the opposite. It's data that has been formatted, usually into rows and columns, following a strict model, precisely to facilitate storage, use, and easy information generation. Think of the transaction records in an operational database, or numbers neatly arranged in a spreadsheet with clear column headers.
Very organized.
Very organized. And then there's a middle ground.
Oh, okay.
Semi-structured data. This is data that hasn't been fully structured into strict tables, but it has been processed to some extent and contains tags or markers to separate semantic elements. A typical web page with its HTML tags is a good example, or an email with its to, from subject fields.
Okay, and managing this semi-structured data led to specific technologies.
Yes. The need to handle semi-structured data, especially for web-based data exchange, led to the development of XML, Extensible Markup Language. XML allows data elements to be represented and manipulated textually using custom tags. And this, in turn, led to specialized XML databases designed specifically for managing large volumes of XML data.
But the really seismic shift, the thing driving massive change right now, has been driven by just exponential growth of social media, sensor data, the Internet of Things. This is the big data era, right?
Yes, absolutely. We're talking about data on a scale that was unimaginable even 15, 20 years ago. You mentioned Google earlier. Think about Facebook ingesting something like 500 terabytes of new data every single day.
500 terabytes a day.
Yeah. Photos, videos, status updates, clicks, likes. It's staggering. Traditional relational databases, which were built for highly structured, predictable transactional data and rigid consistency, they really started to struggle with this flood. They weren't designed for this kind of scale or variety.
And this necessity led to those defining characteristics of big data, the 3 Vs.
Exactly. The 3 Vs have become the standard way to describe the challenge.
Okay, let's define those 3 Vs clearly for everyone.
Okay, first, volume. Just the massive, massive amounts of data being generated and stored, quickly reaching petabytes and exabytes and continuing to grow exponentially.
A huge volume.
Second, velocity. This refers to the incredible speed at which data is growing, but also the speed at which it needs to be captured, processed, and analyzed, sometimes in near real time, to derive value. Think high-frequency trading or analyzing live social media feeds.
Fast data. And third,
variety. The data isn't just big and fast, it comes in every conceivable format. You have structured data from transactions, but also unstructured text, geospatial data, sensor readings, video streams, audio files, social media posts, all mixed together.
volume, velocity, variety, the 3 Vs. And this necessity, handling these 3 Vs, created the demand for NoSQL.
That's right. NoSQL actually stands for not only SQL, which is kind of telling. These are a newer generation of database management systems that were intentionally designed not to be based on the traditional relational model with its strict tables and schemas.
Right.
Because they were built specifically to handle the 3 Vs, they prioritize things like massive scalability across many machines, high availability, fault tolerance, and flexibility in handling different data formats, especially unstructured and semi-structured data. They often relax some of the strict consistency rules of relational databases to achieve that scale and speed.
So they're perfect for things like managing huge web logs or massive amounts of sensor readings or storing vast social media user profiles and connections.
Exactly. They offer flexibility over the rigid structure of relational systems, which is often needed for that kind of diverse, rapidly changing data.
Okay, and just to clarify that common confusion point, where does something like Hadoop fit into this picture? Is it a NoSQL database?
Good question. No, Hadoop itself is not technically a NoSQL database, although it's very often used with NoSQL systems in big data architectures.
So what is it?
Hadoop is primarily a Java-based, open-source distributed storage and computational framework. It consists of 2 main parts: HDFS, Hadoop Distributed File System, for storing massive files across clusters of low-cost commodity hardware, and MapReduce, or newer processing engines like Spark, for running complex computations or processing jobs on that distributed data in parallel.
So it's more about storing and processing the massive file.
Exactly. It's excellent for storing the huge volumes of raw data, structured or unstructured, and then running batch processing jobs on it. It's a critical enabling technology for handling big data, often feeding data into or working alongside various NoSQL databases, which might provide faster real-time access or different data models.
Okay, so we know the problem, that file system chaos, and we know the general solution, the DBMS, managing an integrated database. But before you pour the concrete on a massive structure like a skyscraper, you need a detailed blueprint, right?
Absolutely essential.
And in the database world, that blueprint is data modeling.
That's exactly right. Data modeling is the crucial first step in designing any effective database. It is the process of creating a specific, often graphical, representation, essentially an abstraction or blueprint of the complex real-world data structures that an organization needs to manage for a specific problem domain.
So it's like translating the real world into a structured plan.
Precisely. It acts as the intellectual bridge between understanding the organization's operational needs and actually building the finished physical database that meets those needs efficiently and reliably.
Okay, what must a completed data model blueprint contain to actually be effective? What are the key ingredients?
A good data model needs to deliver three core things. First, a detailed description of the data structure itself, what pieces of data need to be stored. Second, a clear set of enforceable rules to guarantee data integrity, making sure the data stays accurate and consistent. And third, a defined data manipulation methodology, how data can be accessed and modified.
And skipping this blueprint phase
Is a recipe for disaster. Even the most expensive, most sophisticated DBMS software will underperform or even fail if the underlying design, the data model, is fundamentally flawed. Garbage in, garbage out, but on a systemic level.
Okay, let's break down the core building blocks that designers use in these blueprints. We have to start with the things we're actually tracking, right?
Right. The fundamental building block is the entity. An entity represents a person, place, thing, concept, or event about which the organization collects and stores data. And crucially, each instance of an entity must be distinguishable or unique from all others.
So typical examples would be things like customer or product or maybe invoice.
Exactly. Those core nouns that represent the key objects or concepts in the business process.
Okay, so we have entities. Next, we need the specifics about those entities.
Those are the attributes. An attribute is a characteristic of an entity. It describes some property or quality of that entity. So for a product entity, attributes might be things like the product name, its unit cost, maybe the quantity currently on hand.
So attributes are basically the equivalent fields in those old file systems.
They are equivalent in concept, yes. But the difference is that in a data model, attributes are defined formally and globally as part of the entity's structure, not just randomly placed in a file.
Got it. Okay, entities and attributes. Then we need to define how these different entities interact with each other. That's relationships, right?
Exactly. A relationship describes an association among two or more entities. It's how the different pieces of the puzzle connect. We typically define three main types of relationships based on what's called cardinality.
Cardinality, meaning how many?
Yeah, basically how many instances of one entity can be related to how many instances of another entity.
Okay, starting with the most common one, I think, one-to-many.
Right. The one-to-many, one-met-em relationship. In diagrams, you often see this written as one, a classic example. One painter can paint many paintings.
Okay.
But each painting is painted by one and only one painter. That's a one-to-mem relationship. One painter, many paintings.
Got it. Okay, next, the complexity jumps up a bit, many-to-many.
The many-to-many MN relationship, often written as a RIT, this is where things get really flexible and represent more complex interactions. Think about employees and skills. One employee may learn many different skills over their career.
Right.
And conversely, each specific skill, like Java programming or project management, may be learned and possessed by many different employees. That's MN.
Okay, that makes sense. And the simplest relationship.
That's the 1-to-1, 1.1 relationship, written 1.1. These are less common, but sometimes necessary. For example, in a specific organizational setup, maybe one specific store is managed by one and only one employee, the store manager.
And that employee only manages that one store.
Exactly. One store, one manager, one store. A 1.1 link. And it's important to remember, all these relationships are usually defined as bidirectional. They work both ways.
Okay, entities, attributes, relationships. The final building block you mentioned was the constraint. What's that?
A constraint is essentially a rule. It's a restriction placed on the data itself to ensure its accuracy and integrity. Constraints are non-negotiable rules that the data must follow.
Like what? Give me an example.
Okay, a simple constraint might dictate that a student's GPA must always be a value between 0.0 and 4.0, or that a customer ID cannot be left blank, it's a required field. Or maybe that the state attribute in an address must be one of the official two-letter state abbreviations.
So constraints prevent bad or invalid data from ever even entering the system in the first place.
Exactly. They enforce data quality at the point of entry.
Okay, so these building blocks, entities, attributes, relationships, constraints, where do they actually come from? The database designer doesn't just invent them out of thin air, right? They have to be dictated by the organization itself somehow.
Absolutely right. This is where business rules come into play, and they are critical. A business rule is simply a brief, precise, and unambiguous description of a policy, procedure, or principle that exists within a specific organization.
So things the business already does or requires.
Yes. For instance, a business rule might be, a customer may generate many invoices. Or another one, a training session cannot be scheduled for fewer than 10 employees. Or a manager must approve all purchase orders over $5,000. These are statements about how the business operates.
So the designer's job then is to find these rules, understand them, and translate them directly into the components of the data model, the entities, attributes, relationships, and constraints.
That's precisely the task.
How does that translation actually happen? Is there a trick to it?
There are patterns you look for. When you're analyzing these business rules, which often come from interviews with managers, policy documents, or observing processes, you look for the linguistic structure. Generally speaking, the nouns in the business rule tend to translate into entities, like customer, invoice, manager, employee.
Okay.
And the verbs, whether active or passive, that connect those nouns usually indicate the relationships between the entities: may generate, must approve, is scheduled for. The wording of the rule also helps determine the cardinality, one, many, of that relationship.
Fascinating. Okay, and this translation process, understanding these rules and building the model, this is also where having good practice in naming conventions becomes absolutely vital, isn't it? For communication between the designer, the programmers, the end users.
Oh, crucial. Proper, consistent naming is absolutely essential for creating a database that is somewhat self-documenting and easy to understand.
What are some good practices?
Well, entity names should be descriptive, meaningful to the business, and generally singular use painter, not painters. Makes relationships clearer.
Okay.
Yeah, attributes should ideally be prefixed with the entity abbreviation or some standard prefix for immediate clarity. For example, instead of just credit limit, use credit limit for the customer entity or date for the invoice entity. This avoids ambiguity, especially when you have attributes with similar names and different entities, and it makes relationships that use common attributes much easier to identify later, particularly when we get to the relational model. That consistency is just crucial when the model gets complex.
Okay, so data modeling provides the blueprint. But just like architectural styles, data models themselves have evolved over time, often trying to overcome the flaws of whatever came before. Let's trace that history, the major shifts in thinking, starting way back in the 1960s with those early kind of restrictive models.
Right. The earliest widely adopted data model was the hierarchical model. This was developed largely to handle the complexity of large-scale manufacturing systems. Its most famous application was probably for the bill of materials systems used in the Apollo moon rocket project.
Wow, okay, so complex stuff. What did it look like?
It's based on a strict upside-down tree structure. Think of an organizational chart. Data was stored in segments, which were the equivalent of records in the file systems we discussed.
Okay.
But the key limitation was that it could only depict one-to-many 1M relationships, and crucially, each child segment was only allowed to have one parent segment. If you had a situation where something needed two parents, like a part used in multiple assemblies, the basic hierarchical model couldn't represent that directly. It broke the structure.
Okay, very rigid. And that rigidity, that single-parent rule, led directly to the next evolution, the network model, right?
Exactly. The network model was developed specifically to address the limitations of the hierarchical model. Its main advantage was that it allowed a record, or node, to have more than one parent.
So it could handle those more complex many-to-many type relationships.
Yes, it could represent things like a student taking multiple classes, where each class also has multiple students, or parts belonging to multiple assemblies. This was a big step forward in flexibility.
And the network model also introduced some really important concepts that we still use every single day in database management, didn't it?
It absolutely did. Key modern concepts originated here. It formalized the idea of the schema, which is the conceptual organization of the entire database, the overall map.
Okay.
And the subschema, which is the specific portion of the database that a particular application program sees or is allowed to access. This was an early form of providing different views for different users.
And it also gave us the standard languages for actually defining and manipulating the database, right?
Yes, huge contribution. The Network Model Standards Committees, like Codicil, formally defined the data definition language, DDL, used by the database administrator to define the schema components.
Okay.
And the data manipulation language, DML, used by the application programmer to navigate the records and actually work with the data, inserting, updating, deleting. While the network model itself, with its complex pointers and navigation paths, proved cumbersome and still suffered from structural dependence issues,
Right.
the conceptual contributions schema, subschema, DDL, DML are permanent foundations. They live on directly in modern SQL-based systems.
Okay, but both of these early models, hierarchical and network, they were still pretty complex to work with. They required programmers to navigate these intricate data paths, and they still lacked that easy flexibility for those spur-of-the-moment ad hoc queries.
Exactly. They were powerful for predefined processes,
Yeah.
but very inflexible for exploration.
And this rigidity, this complexity, it really paved the way for what most people consider the biggest revolution in data management history.
Without a doubt. The revolution arrived in 1970 with Edgar F. Codd, a researcher at IBM. He published a truly seminal paper introducing the relational model.
Based on math.
Yes, based on mathematical set theory and relational algebra. Codd's genius was proposing that data should not be viewed as interconnected records navigated by pointers, but as simple, independent collections of data called relations, which we usually just call tables.
Tables like rows and columns.
Exactly. Tables composed of rows, which Codd called tuples, and columns, which he called attributes. Simple, intuitive, two-dimensional tables.
Now, Codd fundamentally challenged the established industry, which was heavily invested in those complex procedural network database systems. What made the RDBMS, Relational Database Management System, built on his model so profoundly superior? Why did it win?
Several key things. First, the RDBMS manages the database and completely hides the physical storage complexities from the user. You don't need to know how the data is stored or navigated, you just interact with the logical tables. This finally achieved genuine structural independence.
Okay, huge improvement.
But the true power, the magic of the relational model, is its elegant ability to relate or link these independent tables together simply by sharing common attribute values. For example, you can link a customer table and an agent table if they both contain an agent code column.
So you use a little bit of a controlled, planned redundancy, just storing that agent code in both tables to link massive amounts of data together.
Precisely. It uses this simple mechanism of shared values to efficiently connect information across the entire database, avoiding all the systemic chaos, inconsistency, and anomalies caused by the uncontrolled redundancy in the old file systems.
And the language that came with it, that really sealed the deal, didn't it?
Oh, absolutely. Structured query language. SQL. SQL is a powerful, flexible, and crucially non-procedural query language.
Non-procedural meaning.
Meaning the user only has to specify what data they want. Like select customer names from customers where city of New York. They do not have to tell the computer how to navigate the physical files, indexes, or pointers to get it. The RDBMS figures out the how automatically.
And that made ad hoc queries easy.
It made them a simple reality for non-programmers even. SQL really democratized data access and became the standard language for interacting with relational databases. It still is today.
Okay, and complementary to the relational model itself was the design tool, the graphical blueprint you mentioned earlier, the ER model.
Yes, the Entity Relationship Model, ERM, introduced by Peter Chen in 1976, provided the perfect conceptual framework and visualization tool for designing relational databases.
How does it work?
It uses the Entity Relationship Diagram, ERD, as the graphical blueprint. The ERD visually shows the database's main components. The entities, usually drawn as rectangles, and the relationships between them, drawn as lines connecting the rectangles, often with symbols indicating the cardinality.
So it's the picture of the blueprint.
Exactly. It became the standard way for designers, developers, and business users to communicate about and refine the database design before building it. There are a few different notations, like Chen's original notation, but today we most commonly use something like crow's foot notation.
Crow's foot.
Yeah, it uses a little three-pronged symbol, looks like a crow's foot, on the line to clearly indicate the many side of a one-to-many or many-to-many relationship. It's very intuitive.
Okay. So the relational model dominates. But as data started to grow beyond simple text and numbers to include more complex stuff, like multimedia, video, complex scientific data, even the relational model had to evolve again, didn't it, to handle these richer data types?
It did, yeah. The next major influence came from the world of object-oriented programming. This led to the object-oriented data model, ODM.
Object-oriented, how does that apply to databases?
In the ODM, both the data, the attributes, and its relationships, plus its behavior, the procedures or code that operate on the data, are contained together in a single structure called an object.
Okay, so it's not just data anymore, it's data plus what you can do with it.
Exactly. Think of an object not just as a passive record storing data, but as a mini program. A customer object wouldn't just store the address, it might have a calculated discount method built right into it.
Ah, okay. So instead of just storing, say, a car's color as an attribute, the object-oriented car object might actually know how to drive itself, hypothetically, through a drive method.
Precisely that kind of concept. These objects are then grouped into classes, which define the structure and methods for similar objects. And these classes can form a class hierarchy allowing inheritance.
Inheritance.
Meaning a specific type of object, like a sports car object, automatically inherits all the basic attributes like color, wheels, and methods like start engine from its parent car class, and then adds its own specific ones like retract truth. It promotes reusability.
Okay, that sounds powerful, but maybe quite different from tables. Did the relational world just give up?
No, not at all. The relational vendors responded, too, by incorporating many of these object-oriented concepts into the relational framework. This created the dominant model we see in most major databases today.
Which is?
It's often called the Extended Relational Data Model, ERDM, or sometimes Object Relational. The systems that implement it are called Object Relational DBMS, or DBMS.
So, kind of a hybrid.
Exactly. These systems maintain the core, simpler, and well-understood relational table structure, which is great for many standard business applications, but they add ODM features like support for complex objects, user-defined data types like geographic coordinates or multimedia types, and sometimes inheritance. The ORDBMS remains the currently dominant database solution for most standard OLTP and complex OLAP applications.
Okay, and finally, that brings us right up to the current major shift, dealing with big data and the consequent rise of NoSQL.
Right. As we discussed with the 3 Vs, the sheer imperative to manage the unprecedented volume, variety, and velocity of web, mobile, social media, and sensor data, it simply broke the ability of even the most extended relational systems to handle the scale, speed, and flexibility demands simultaneously.
Why? What's the fundamental mismatch?
Relational systems are fantastic when you need rigid consistency, ACD properties, and when you know the structure of your data perfectly upfront, defined in a strict schema. They enforce that structure rigorously.
Which is good for financial transactions?
Absolutely essential.
Right.
But for the messy, unpredictable, massively scaling world of big data, that rigidity becomes a bottleneck. You might not know the exact structure of the data coming in, or it might change constantly. Trying to force it into predefined tables can be inefficient or impossible at scale.
And so NoSQL systems essentially sacrifice some of that rigid structure and consistency for massive speed, scalability, and flexibility.
Correct. That's the trade-off. NoSQL systems are specifically designed for high scalability, often running on hundreds or thousands of commodity servers, high availability, and fault tolerance in a distributed architecture. They are perfect for data that might be sparse, messy, schemaless, or constantly evolving, exactly the kind of data you get from web traffic logs, social media feeds, or vast IoT sensor networks. The sheer scale and variety demanded solutions that weren't tied to the strict table structure and consistency guarantees of COD's original relational model.
Okay, so if we accept the data model as the essential blueprint for any database, we also need to understand that the blueprint itself isn't just one single drawing. It actually has different levels of detail, different perspectives depending on who is looking at it and what they need to see.
That's a really important concept, yeah. This idea of different levels of data abstraction is standardized, more or less, by the ANSYS-PARC framework, which defines the different views or levels of the data.
Why do we need different levels?
This progression, moving from a high-level overview down to the nitty-gritty details, is critical for managing complexity. Think of it like designing a complex custom house. You start with the architect's initial sketch or concept drawing. That's the high-level conceptual view.
Right, just the overall layout.
Before you move to the detailed engineering blueprints showing all the structural supports, that's like the internal view, and then finally the precise electrical wiring diagrams and plumbing specs. That's down at the physical view. This framework defines 4 main levels, moving logically from the human end-user view down to the machine's storage view.
Okay, let's start at the highest level then, the most human-centric view. That's the external model, right?
Correct. The external model represents the end-user's view of the data environment. In any reasonably large organization, the entire database is just too complex for any one person or department to grasp or even need to see all at once.
So different people see different parts.
Exactly. Each business unit, maybe the sales department, the accounting department, the class scheduling office, typically sees and interacts with only a specific, necessary subset of the organization's total data. This specific, tailored representation that meets their particular needs is called an external schema.
Okay, so using the tiny college example from the book, the registrar's office might see the student registration view, focusing on students, courses, and enrollment records.
Right.
While the accounting department might see the finance view, focusing on students, tuition fees, and payment records. They might share the student entity, maybe the course entity, but their primary concerns and the relationships they focus on are entirely different.
Precisely. And this approach has massive advantages. For one, it makes it much easier to identify the specific data requirements for each business unit. It simplifies application development because programmers only need to worry about the subset of data relevant to their application.
And security.
And it significantly helps with security and data integrity. If users only interact with a controlled subset of the data through their external view, accidental or malicious damage or corruption to the whole database becomes much harder. It compartmentalizes access.
Okay, that makes sense. Step 2 then, pulling all those different specialized subsets, those external views, together into the definitive organization-wide map. That sounds like the conceptual model.
That's exactly what it is. The conceptual model represents the global view of the entire organization's data. It integrates all those different external views into a single, coherent, unified conceptual schema. It's the big picture of all the entities, attributes, relationships, and constraints for the whole enterprise.
And this is where the ER model and the ERD that we talked about really shine, right? As the main tool for building this big picture.
Yes, the ER model ERD is the most widely used tool for developing and documenting the conceptual model. It provides that technology-independent blueprint.
And you say technology independent. This model is revered because it's completely independent of whatever specific database software or hardware you eventually choose to use, isn't it?
Precisely. That's a key feature. The conceptual model is designed to be both software independent and hardware independent. It provides the pure logical structure of the organization's data without caring if you're going to implement it using Oracle or PostgreSQL or Microsoft SQL Server, or whether you'll run it on a Linux server, a Windows server, or in the cloud. This phase of design, creating the conceptual model, is often called the logical design of the database. It's about the what, not the how.
Okay, pure logical structure. But eventually, we do have to choose the technology, right? We have to pick a specific DBMS. Once we've made that choice, say, we commit to using a specific relational DBMS like Oracle, we move down to the third level, the internal model.
Correct. The internal model takes that abstract technology-agnostic conceptual model and maps it to the specific characteristics and constructs of the chosen DBMS.
Like it's more concrete now.
Yes. The internal schema, which represents this model, is expressed using the specific database constructs provided by that particular DBMS software. For a relational DBMS, this would mean defining the actual tables, the columns with their specific data types, like varchar2 in Oracle or INT in SQL Server, the primary and foreign keys, the indexes, the views, all expressed using the specific SQL DDL of that chosen system.
Okay, so the internal model clearly sacrifices that software independence we had at the conceptual level, but it gains precision for a specific implementation.
Exactly. It becomes software dependent. If you decide later to switch from Oracle to PostgreSQL, you will likely need to change the internal model to match PostgreSQL's specific features and syntax.
But does it keep any independence?
Yes, crucially, it still retains logical independence. This means you should be able to change aspects of the internal model, maybe optimize the table structures, add or drop indexes to improve performance without having to change the overarching conceptual model, the big picture logical design. It's also still generally hardware independent at this stage. The internal schema describes the database as seen by the DBMS software, not necessarily how it's laid out on physical disks yet.
Okay, and that brings us to the final, deepest level of abstraction, the one that defines exactly where the bits and bytes are actually stored. This must be the physical model.
That's right. This is the lowest level of abstraction operating closest to the hardware. The physical model describes how the data is physically saved on the storage media, whether that's magnetic hard drives, solid-state drives, SSDs, or cloud storage volumes.
So this is really low-level stuff.
Very low level. It requires defining the physical storage devices themselves, the file paths, the access methods, how the operating system reads and writes the data blocks, deciding on data compression, partitioning strategies, and so on. Because of this necessary level of detail about the storage environment, the physical model is inherently both software dependent, tied to the specific DBMS and OS, and hardware dependent, tied to the specific storage devices.
And the main goal here is just performance optimization, right?
Yeah.
Ensuring the fastest possible access times for the specific hardware configuration that's actually in use.
Exactly. Tuning the physical model is all about performance. But the real beauty of this whole layered ANSYS Spark framework, this progression of abstraction, is the independence it provides between the layers. If you can change the physical model, maybe upgrade your hard drives to faster SSDs, or switch the underlying operating system without affecting the internal model the way the DBMS sees the tables, then you have achieved physical independence. This layered abstraction, with logical independence between conceptual and internal, and physical independence between internal and physical, is what gives modern database systems their remarkable flexibility, resilience, and maintainability compared to those old monolithic file systems where everything was tangled together. #TechOutro. So, we've really completed a significant journey today. We've traced the technological evolution all the way from those simple, often unreliable manual file folders, a process just riddled with systemic errors like structural dependence and those crippling data anomalies.
Yeah, the update, insertion, deletion ones.
Exactly. All the way through to today's complex distributed big data architectures handling petabytes. But the central enduring takeaway, I think, is that successful, efficient, and truly reliable database systems rely entirely on thoughtful design defined by those architectural blueprints. The data models we discuss, they don't happen by luck.
Absolutely. And for you listening, hopefully, we've helped clarify that fundamental difference between just raw data, then contextualized information, and finally, predictive knowledge.
Right.
We saw why bad design, particularly in those early file systems, created such critical failures. Those anomalies like update and deletion problems that basically meant you couldn't trust your own data half the time.
Mm-hmm.
The solution was the DBMS, managing metadata, acting as that intermediary, and introducing key concepts like ad hoc query capability and, crucially, controlled redundancy through things like the relational model.
And we saw how the blueprints themselves, the data models, evolved from the rigid hierarchical and network models aiming for structure but lacking flexibility to the elegant stability and query power of the relational model, which still dominates. And then finally adapting again to handle the massive scale and complexity of the 3V's volume, variety, and velocity with the emergence of NoSQL systems for specific big data challenges. Understanding these different models, and especially those layers of abstraction from external down to physical, is really what separates a knowledgeable database professional from someone just, reading a technical manual.
Yeah, and the need for professionals who truly understand these fundamentals is just accelerating, isn't it? Whether you're aiming for a role as a database administrator, a GBA, or maybe the database designer or cloud computing architect managing these systems, or perhaps a data scientist trying to extract insights from those vast data pools. The core concepts we discussed today, entities, attributes, relationships, normalization, which we didn't even get to, the levels of abstraction, they remain the absolute bedrock of our digital infrastructure, even as the specific technology itself evolves at breakneck speed with VLDBs, in-memory databases, cloud platforms.
The fundamentals persist. And, this brings us maybe to a final provocative thought that connects all this technical structure right back to our everyday lives.
Okay.
We noted that modern technologies like NoSQL, combined with powerful analytical databases and machine learning, allow organizations like Amazon or Google or Netflix to leverage truly massive amounts of behavioral data about us.
Yeah, our clicks, our views, our purchases.
Everything. And they can perform analysis that leads to things like predictive shipping, where Amazon might literally send you a product before you even consciously realize you need it, based purely on analyzing your past data patterns and those of similar users.
Wow, that's knowledge derived directly from our maybe even unconscious behavior.
It is. So the question to ponder is this. If organizations can derive this level of sophisticated predictive knowledge about our future needs, our desires, our habits, what does this exponential rate of data generation and analysis truly imply for our own sense of free will, our privacy, our future consumer autonomy? As we continue to generate data faster and faster, often without even thinking about it, how much actual control over our future decisions do we really retain when the very systems we use might already know, statistically speaking, what we're going to do or want or buy next?
That's a profound question. Something definitely worth exploring on your own after this.
Indeed.
Well, this has been a fascinating and truly essential dive into building the foundations of our digital world. Thank you so much for walking us through it.
My pleasure.
And thank you for joining us for this deep dive.